Okay. Taylor series, Taylor expansion, there's lots of different names that you'll find attached to this thing, but Taylor is the key word there. Taylor series or Taylor polynomials, I know that you haven't done or at least most of you have not done the single variable form. That's fine. I'll talk about single variable and multivariable. Taylor series or Taylor polynomials or Taylor expansions have got a bunch of names. Are polynomial representations of functions. Okay? There's always one point on the actual function, the true function that we are approximating with our polynomial. There is always one point on the function which matches the polynomial exactly. Okay, and I'm going to give a little footnote to that word exactly in a moment, which we call x equals a. So I'm starting off with single variable Taylor polynomials here, and then I'll move on to two variables. Okay, but then here's a little footnote. By exactly, I mean as much as the degree of the polynomial allows. Okay? So basically, if you think of a sine curve, and I think we've actually, I'm getting a bit of deja vu here. Did we talk about Taylor series a few weeks ago? Think of a sine curve, and think of trying to approximate a sine curve with a polynomial. Let's start off with a first degree polynomial. A first degree polynomial is just a line. And let's say we're trying to approximate sine x at the origin. So here's my sine curve. Okay. If I'm trying to approximate my polynomial with a straight line here at the origin, it would have to be like that. Okay, so that would be my first degree approximation. Pretty lousy approximation if you get very far from the origin. If you only go a smidgen away from the origin, it's not too bad. And of course, that would be what we would call the linearization of sine x at 0. It's the tangent line at 0. It has a number of different identities. But it is also the first degree Taylor expansion of sine x at 0. Okay, then what about second degree? What about a parabola? What about trying to approximate it with a parabola? It turns out, in this particular example I'm using here of sine x, a parabola actually doesn't work. It breaks down. You can't approximate sine x with a parabola, but you can with a cubic. Because what you can get is this sort of thing. That would be the third degree approximation. And that's not too bad, because a third degree polynomial, a cubic, has two bumps in it. And so you can approximate two of the bumps in the sine x graph with your cubic. But of course, so therefore, you can get further away from the origin and still have it be an okay approximation. But beyond a certain point, it becomes a grotty approximation again. And you can keep adding degrees to your polynomial. Turns out fourth degree is not very good for sine x, but fifth degree is pretty good. Fifth degree, you can approximate 4 bumps. Okay, so with a fifth degree, you can have something that looks like this. Wow. The fifth degree approximation can kind of incorporate in its shape 4 of the bumps of the sine x curve. Yes, well, if you think about it, when you're solving for the turning points of a polynomial, you differentiate and set your derivative equal to 0 to find where your tangent is horizontal. So by taking an nth degree polynomial, the expression that you end up solving for those turning points is always an n minus 1th degree polynomial because of the process of differentiation. So, but if you just think from your own common experience, an nth degree polynomial can have at most n minus 1 turning points. You're very closely familiar with parabolas and cubics, but that pattern holds as you go up as well. Okay, so that's just my little rough, scruffy diagram to show the sort of thing that Taylor polynomials do. Taylor polynomials are polynomials. Taylor expansions are polynomials. And polynomials are great. They're wonderful to work with. They're so easy to integrate. They're so easy to differentiate. They're so easy to calculate anything in because fundamentally they're just about timesing and dividing. So polynomials are very easy, flexible, useful formulas to work with. And so it can be very convenient to approximate non-polynomial functions as polynomials. So that's what Taylor series do. Very useful things. You can use them in a variety of different contexts. So there is a general formula for a polynomial. Given some function, how do you find its polynomial approximation? And that's what we're going to derive now. So I'm going to derive it pretty fast. Assume such a polynomial exists. And takes the form f of x is, so f of x is our actual function. It's our log or our sine or our exponential, or it's the thing that's not the polynomial. And it's approximately equal to some constant plus some constant times x minus a plus some constant times x minus a squared plus some constant times x minus a cubed plus on it goes. Okay, so we're assuming, so that's a polynomial. That thing I've written down there is a polynomial. The thing on the right. And we're putting dot, dot, dot because we're assuming that it can go on forever. All right. Now if we plug x equals a into the left and right hand sides of that equal sign of that expression, everything on the right disappears except for the c naught. So c naught is just f of a. So now we've got the first term in our polynomial approximation of our function. What if we differentiate our function? The c naught's going to disappear. We're going to be left with c1 plus 2c2 x minus a plus c3 x minus a squared plus the higher order terms. Once again, plug in x equals a on both sides. F dash of a equals c1 and the rest of the terms are 0. We now have the second term in our polynomial expansion. Okay, looks like there's a pattern there, but the apparent pattern is about to break down. Second derivative. I'm going to differentiate, yes?
Is it 0 because x is equal to a?
Yes, because x is equal to a. So we're plugging x equals a in on both sides. On the left-hand side, that simply means putting an a in the brackets of our function expression. And on the right, it means plugging a in everywhere there's an x, and then all the terms that have an x minus a end up being 0. And using that and just keeping on differentiating and differentiating and differentiating, we're able to get what our terms look like as we go up in degree of our polynomial expression. So second degree will be 2c2 plus, now this is going to look funny, but instead of writing 6, I'm going to write 3 times 2. Because I'm wanting a certain pattern to be apparent. If I plug in x equals a, once again I'll just get 2c2, which implies that c2 is f double dash of a over 2. Third derivative with respect to x is going to be, well, it's 6c3, not x minus a, plus dot dot dot, and of course the other terms after that plus, they still have x minus a's in them. So when I plug in a, I'm only left with the 6c3, which implies that c3 is equal to triple dash f triple dash of a over 6. And if you remember where that 6 came from, it was a 3 times a 2. Think about the next term that I haven't written. It would have started off with the power 4. I would have had a 4 come down, and the next derivative of 3 would have come down, and the next derivative of 2 would have come down. And so the next term would have been the fourth derivative over 4 times 3 times 2 times 1. We can see that C4 would be the fourth derivative evaluated at A over 4 times 3 times 2 times 1, because it's that pattern that you get when you differentiate a polynomial over and over. You bring down the power, next time you bring down 1 power less, next time you bring down 1 power less, and that denominator, that pattern of a number times a number less, times a number less, times a number less until you get to 1 has a name, and it's called factorial. So this is f of 4a over 4 factorial. This is third derivative over 3 factorial. This is second derivative over 2 factorial, which of course is just 2 times 1. It does look like 41. Looks in fact an awful lot like 41. There we go. And in fact the 3 factorial is not much better. There we go. In general, catch up with me, stylus. Hello? In general, the nth constant is the nth derivative evaluated at a over n factorial, and our polynomial expansion is f of x is approximately equal to the sum of all such terms. From n goes from 0 to infinity of the nth derivative a over n factorial x minus a to the n. Let's just think about the n equals 0 case. The n equals 0 case, we've got x minus a to the power 0, that's just 1. We've got a 0 factorial. 0 factorial is defined as 1. By definition, but there are various ways one can justify that definition by interpreting a factorial as the number of ways of choosing so many objects from so many objects. And how many ways are there of choosing zero? How many ways are there of arranging 0 objects? Well, you can kind of justify it that the definition is 1. But fundamentally, 0 factorial is defined as 1. And of course, the 0th derivative would just be the function itself. You haven't differentiated it yet. Okay, and that's Taylor polynomial. Ta-da, there it is. And now you can use it. You can say, okay, if I want to derive the Taylor expansion of sine x at 0, I can then just differentiate sine x a bunch of times, plug in x equals 0, and you can see what's going to happen there. The even derivative options there would be sine x and minus sine x, would whiffle between sine and minus sine x. Think about it. You'd have sine, you'd differentiate to get cos, you'd differentiate to get minus sine, you'd differentiate to get minus cos, you'd differentiate to get back to sine again, and your derivative would flip between cos and sine with a minus popping in now and then. And all the sine ones would give you 0, and all the cos ones would give you 1. And the cos ones are your first derivative, your third derivative, your fifth derivative, your seventh derivative, etc. Which is why, back in my original little picture, I only bothered drawing the odd degree approximations, because in fact when you actually do the calculations you find out that your even degree terms are all just 0, because you're working out sine at 0. Anyway, if you'd done this in first year, you would at this point have derived the Taylor expansions for all the popular ones. Sine x, cos x, e to the x, and ln of 1 plus x. And they're probably in a box in your textbook, actually. So sine x, cos x, e to the x, and ln of 1 plus x are the, shouldn't say popular, that doesn't sound good. I don't know, most useful, perhaps most encountered, but let me say most useful, are the most useful Taylor expansions in single variable. and they're bound to be listed somewhere in your textbook. You can find them in your textbook, and there actually is a single variable exercise in the handbook. It's number 6 in that. We've started chapter 4. Page 73 is where we are, and number 6 is actually a single variable one, just put in there for some fun. And it's multiple choice, which means it must have come out of the 2010 exam paper, because that's where all of the multiple choice questions here come from. Okay, I think there's much more I want to say. Oh, here are a couple of things. So Taylor expansions so it's nice to think that the more and more terms you put in, the better and better the expansion gets. And as a sort of a base rule, that is true. But there are limitations to Taylor polynomials. For instance, functions that have kinks in them. Polynomials cannot do a very good job of approximating a kink, because polynomials are curvy by their nature. So it doesn't really matter how many terms you put in. There's a limit to how well you can approximate a kink. And you can actually get sort of computer programs where, these sort of graphic programs where you can approximate, you can say, okay, what's a Taylor polynomial up to 20 degrees look like, up to 100 degrees, what does it look like, etc. And if you're trying to approximate something that has a kink, you can make some quite weird spiky effects happen wherever there's a kink, where the polynomial's doing its best to approximate something that it just can't, and it fails. So there are limitations to Taylor polynomials. Also, in certain cases, you'll find that there's a certain distance, so there's always one point where you're approximating stuff, and that point is always the closest, the best approximation, and then as you move further away from that point, the approximation gets a bit wibblier. And we like to think that the more terms we put in, the further away you can go. And that's not always true. Sometimes there's only a certain distance from your point of your sort of point of tangency, if you will. There's only a certain distance away that you can get from it and actually rely on the approximation getting better and better. And you get terms like radius of convergence and stuff. And if we were doing this in Maths 1000, we would talk about that quite a lot, and we would work out the radii of convergence, and we would deal with remainder terms and size of error and all sorts of funky stuff. But we're not doing Maths 1000, so I'm just telling you that. Basically, terms and conditions apply. There are limitations to this method, and there we go. Okay, but fundamentally, as a sort of a baseline, the more terms you put in, the better it gets for a greater distance away from the point of tangency. As a rough rule of thumb, you can work with that. Oops, I don't think I meant to do that. So that was single variable. In fact, let's actually move to a new page, because I'm about to start 2 variable. Okay, so now okay, now, won't write that down. We now extend. So if you'd done that back in first year, you would have done pretty much exactly what I just wrote, and then you would have done some exercises actually deriving. Your lecturer would probably have derived cos x for you and then told you to derive sin x, or the other way around. And then you would have been told to memorize them all, because they all have a very strong pattern to them. So you could memorize them very easily. I mean, I can give you sin x and cos x straight off the top of my head without thinking about it. The others I need to think about a little bit more. E to the x is a combination. Ln 1 plus x is missing the factorials. Interesting effect that goes on there. But they've got a very strong pattern, so you can memorize them very easily. So your first year lecturer would have told you to memorize them, and then you would have got some question in the exam where you would have had to actually plug in the Taylor polynomial of one of those. There you go. That's what your past would have looked like. But we're now moving on to your present, which is 2 variable Taylor series. We now extend this whole idea to functions of more than 1 variable, well, strictly speaking, 2 variables. Such as, and I'm giving you 2 functions here, which will be the 2 that I'll look at immediately after we've done the derivation. Okay, I'm doing too much talking. I need to get to examples. Okay, I'm going to do quite a lot of writing now, and I'm going to give you the basic idea. My basic idea is I'm going to turn my two-variable function into a function of only one variable. Then I'm going to take advantage of the single variable Taylor series, and then I'm going to pop back into two variables. That's what I'm about to do. Let's jump in. Consider f of x, y. Oh, golly. Sure. It's quite frightening. X, y. There we go. Let x be a plus th, and let y be b plus tk. Here's my sneaky way of making my function a function of t only. Let g of t be what I get if I plug those into my f. And g of 0 would then be f of a, b. And the point at which my point of tangency is going to be x equals a, y equals b. Whereas in the single variable, I just had to specify my x. Now I have to specify my x and my y. By the chain rule, so now I'm going to differentiate just like I did a page up. But it's going to require chain rule because f is explicitly a function of x and y and only implicitly a function of t. G dash of t is this thing. This is chain rule. I'm differentiating with respect to t, so it means I need to differentiate with respect to x and then times by dx by dt, plus differentiate with respect to y and then times dy by dt. dx by dt is h, dy by dt is k. Now I'm going to plug in zeros. This is exactly the same idea as a page up. It just looks a bit more complicated because there's chain rule involved because it's a function of two variables. So there we go. I've got g of 0, I've got g dash of 0. Let's work out g double dash of 0. The second derivative, now the second derivative starts to get hairy. Higher order chain rule. Okay, so I'm going to take my first derivative and I'm going to differentiate it with respect to t, but differentiating with respect to t means differentiating with respect to x and then timesing by dx by dt, plus differentiating with respect to y and then timesing with dy by dt. So that's what's written down there. dx by dt is h, dy by dt is k. So now when I differentiate g dash with respect to x, I'm not going to spend too much time on this because we really pushed for time and I think all of us would like to finish this week. So these notes of course will go up on Vula, so you can either copy them down nice and fast now or you can wait, but if you go through them at your leisure, because you have so much leisure time, don't you, then hopefully it'll all make sense. I'm sorry if it seems confusing. It's fundamentally just differentiating. It's just chain rule. But you know from when we did higher order chain rule a few weeks back that it can look rather scary. And now I'm plugging in 0 again into my t. It's just chain rule. Lots and lots of letters, but it's just chain rule and we're not scared of chain rule. It's so little and we're so big. It's like being scared of an ant. Let's not carry the analogy too far, because some small things are scary. Me, for instance. Okay, all right. So what we are doing here is constructing okay, I'm going to use a word I haven't used yet, but I'll describe it. The Maclaurin series. Maclaurin series. What's Maclaurin series? Maclaurin series is Taylor series where we've set the point of tangency to 0. It gets a special name. That stuff that we did in the first page, that single variable stuff where I just kept it as generic x equals a. If x is 0, we give the Taylor series a special name and we call it a Maclaurin series. I don't actually know why. You probably find that 2 different people were working on this simultaneously, and so they kind of share the name. The history of maths is rife with things like that. So what we are doing is we're constructing the Maclaurin series for g, because g is a function of one variable. And g of t, according to single variable Taylor series, is g of 0 plus d dash of 0 t plus a half g double dash of 0, that's a g, t squared plus, that's single variable Taylor series. That's single variable Taylor series where we're plugging into that sigma. That sigma that we had down at the bottom of the first page of notes, where instead of a we've got 0, instead of f we've got g, and instead of x we've got t, but that's what we've got. And I'm only going to go up to second order, and then we can be sneaky and let t equal to 1. Okay, sure. Why would we want to do such a thing? Well, if we let t equal to 1, then g of 1 is really, oops. If we remember what g is, it's f with those x's and y's with the t's in plugged in. And g of 0 is f of ab. We worked that out. G dash of 0 is, okay, now we don't, strictly speaking, need brackets because it's terms being added, but I'm putting in the brackets just to show grouping. Plus, and then a half of g double dash of 0, which we worked out to be h squared xx ab plus 2hk fxy ab plus k squared fyy ab plus dot. Sorry, I ran out of space for my dots there. They should be horizontal dots. They shouldn't be vertical dots. But I ran out of space. And ta-da! That's our formula. So I'm just going to tidy it up a little. So f of xy is approximately equal to f of ab plus, okay, now instead of h, I'm going to write x minus a. Which way is it written in the box over there? Yeah, I just want to make sure I'm writing it in the same way. And what I'm writing now is in the box on page 73 of your handbook. And this formula you have to memorize. But there's a pattern to it. There's a very strong pattern. Oh, there's a mistake in my notes here. Oh dear. HOT, higher order terms. There's a very strong pattern to that. You can remember that. You can remember that. You can totally remember that. Come on. You can remember like all the lyrics to your favorite pop song. You can remember this. Who here knows all the lyrics to at least 4 songs? Go on. Go on. Ah, you're lying. All of you do. You can remember Taylor series. So we have the actual function value, okay? Just one of them. Just one term related to the actual function value. Then we have 2 terms related to the first derivative because there are 2 first derivatives. There's the x derivative and the y derivative. The x derivative gets x minus a and the y derivative gives y minus b. It's fine. Then we have 3 terms related to the second derivatives because there are actually 4 second derivatives, but 2 of them are always the same. The yx and the xy. Okay? So in a sense, we have 3 second derivatives, so we have 3 terms. The xx gets x minus a squared, The yy gets y minus b squared, and the xy gets x minus a and a y minus b. And in a sense, they all have a half coefficient, but the xy also has a times by 2 because there's two of them that are the same, and so that half and the 2 cancel out. So there's a pattern here, and it's not a hard pattern to remember, and there you go. But even if it is a hard pattern to remember, the sad truth is you do need to memorize it. Okay, question at the back? Yes, you substitute everything in and work it out, and I will demonstrate with an example number 1. Question over here, yes? I beg your pardon? Yeah, sure. Is that fine? Okay, I'm going to demonstrate with exercise 1 from the handbook, and it really is easy. You might look at that and think, wow, this is so hard. It's not. It's actually quite an easy formula to memorize once you set your mind to it, and all you have to do is work out a bunch of derivatives and plug it in. If you get one of these in the exam, you should say, oh, hooray, marks in my pocket. In fact, anything in this chapter 4 is marks in your pocket. Okay, so what do we got? We've got the actual function. And I'm going to work out a bunch of derivatives. Actually, if you don't mind, I'm going to go on to the next page, because this is all the space I've got here, and I'd like to have it all together. So let's try again. F of xy is e to the xy squared. Let's work out the x derivative. X derivative will be y squared e to the xy squared. Y derivative will be 2xy e to the xy squared. X derivative, double x derivative. I now need to take my x derivative and differentiate it with respect to x again. Well, product rule, sure, except not in this case, because the product of those two functions, the one function doesn't have x in it. But keep product rule in mind, because we are going to use it. But as far as x is concerned, y squared is just a funny looking constant, so we're going to end up with y to the 4 to the xy squared. Now what about the xy derivative? Xy derivative, I'm going to take my x derivative and differentiate with respect to y. Okay, now product rule. 2y e to the xy squared plus 2xy cubed e to the xy squared. I differentiate the y squared to get 2y, and the exponential just comes along to keep it company. Plus, in the next term, the y squared is just coming along, and the e to the xy squared is the one getting differentiated, which involves bringing down a 2xy. So I get a 2xy cubed. Okay, my y derivative. Okay, here's a way of checking yourself to actually work out the yx derivative. The yx derivative should be the same as the xy derivative, but if you made a mistake in your two first order derivatives, that mistake might now show up if your xy and your yx are not the same. Yy will be, again, product rule. Let's have a look. I'm bringing down a 2xy, so it will be 4x squared y squared e to the xy squared. Phew, okay, that's everything I need. Now I'm going to plug in the point. I've been given the point 2, 1. F of 2, 1. I tend to do it in 2 columns like this. 2, so that'll be e squared. F x at 2, 1 is going to be also e squared. Y derivative, I keep writing x, y, not 2, 1, is 4 e squared. The xx derivative is e squared. The xy derivative is 2e squared plus 4e squared, in other words 6e squared. And the y derivative is 4e squared plus 2 squared is 4 times 4 is 16, 16e squared. So my Taylor polynomial is f of xy is approximately equal to, wiggly equal signs, e squared plus x minus 2 times by e squared plus y minus 1 times by 4e squared plus a half x minus 2 squared times e squared plus x minus 2y minus 1 times 6e squared plus y minus 1 squared times 20e squared plus higher order terms. Higher order terms which would all include e squared. So you can simplify this a little if you want. By pulling out the e squared. And of course you could multiply out those little brackety things and actually simplify quite a lot. And I think in my solutions I did do that. But you don't have to. Leaving it like this is fine. Let me put a nice big red tick. If you leave it there, that's fine. Okay, if it's really, sometimes you get ones where lots of the terms are 0, a lot of the coefficients are 0. And then simplifying it into something that actually looks nice and neat without any brackets is quite an easy job to do, in which case please do that. I'll answer your question in a second, just let me write that down. No need to simplify unless simplification is easy and obvious, in which case please do. Question?
So majority of the marks are just about
Yeah, look, you wouldn't get a lot of marks for this. You'd get maybe 3 marks for getting the derivatives right.
and then a question like this would be out of
5 maybe. It wouldn't be a lot. I'm guessing there. I don't know. Look in old exam papers and see. I'm guessing there. 6 is really pushing it. I would guess 5. Yeah. Question?
Why do we not have 10 e squared instead of 20 e squared?
Yeah, you're right. I lost my half, didn't I? I lost my half because I'm in such a hurry. So that's actually a 10. Thank you. Okay, what I would like to do is another example and then give you an opportunity to do one, but why in fact don't you do that? Why don't you try number 2? You try number 2. Yeah. There's only a few minutes left of the period, but why don't you try that? And then tomorrow I'd like to start on max min. I don't think we have... There's another question? Yes? Sure. Where did I say so? On the previous page? So, there we are. Is that fine? Okay, so you give number 2 a try. I think I'm still recording. Let's have a look. Does it simplify to something nice? Does it? Let me just look through my notes quickly. Yeah, 2-1 simplifies to something rather nice. And 2 a little bit more complicated if you multiply it all out. There's a lot of halves involved here. That's for number 2.